Okay, geometry, we have just two last theorems to look at here as we finish out Unit 6. We're going to be looking at parts of similar triangles, and then we're going to be also digging a little bit deeper into the angle bisector. So first off, if two triangles are similar, then their corresponding parts are also proportional. This should hopefully make sense. All of their sides are in proportion, so their special pieces should also be. Our first one is an altitude. So we create an altitude by going from a vertex down to a right angle. So you've also seen this called the height of a triangle, like when you were calculating area in middle school. So anytime we're going intersecting a vertex and then we're intersecting the opposite side at a right angle, then that is an altitude. So we can put a proportion here. We could say that altitude BD over altitude FH is equal to, and then we just pick any two corresponding sides. So maybe I'll say BC over FG. Okay. The next one would be an angle bisector. So an angle bisector goes from a vertex to the opposite side, and it intersects that vertex angle at it cuts it exactly in half. We've seen these before. And if you have two similar triangles, then their angle bisectors to corresponding angles are also in proportion. So again, we've got these angle bisectors. We can say QS over UW is equal to, and then we just have to pick two corresponding sides. So maybe I'll say QP over UT. Okay, and then our last one is a median. So a median intersects a vertex and the opposite side of a triangle at the midpoint. So a median always cuts that opposite side exactly in half. And if we have two similar triangles, then their medians are also in proportion. So for example here, we could say HJ over LN is equal to HG over LK. So these proportions hold, and part of the reason, just to kind of look into it, is if we look at the smaller triangles here, so we've got triangle ABC and EFG are similar to each other. Well, that also means that triangle BDC and FHG, if we look at the smaller parts, or the smaller triangles inside the triangle, those are also going to be similar to each other. So that's why these proportions hold up. Okay, let's just do like one example here. We've got given similar triangles and we want to solve for x. So let's see here. We've got these medians here in number one, and it looks like we've got SW is what we want to solve for. So SW is x units long, and then the other median in triangle DEC is 15 units long. And then we just need to pick two corresponding sides. So let's see, I've got TS here, which should line up with ED. So TS is 16 and ED is 20. And the reason that I know those two are the corresponding parts is from this similarity statement, STDE. They're the first two letters of each of these triangles. Okay, and from here we just solve. So we cross multiply. When we do that, we get 20x is equal to 240, and that means that x is equal to 12. So that's our answer there. X is equal to 12. And I'm going to have you finish the rest of these, but just use the similarity statement to find the matching parts, find the corresponding parts, because these are rotated around a little bit, so just make sure you're grabbing the correct parts. Okay, now we're going to look at our last theorem of this unit, and it's the triangle angle bisector theorem. So this is kind of interesting. This does not really have to do with similar triangles, but it does have to do with proportion. And this says an angle bisector in a triangle separates the opposite sides into two segments that are proportional to the lengths of the other sides. So what this is actually saying is that AD over DC, so AD over DC is equal to AB over BC. And this only works if we have an angle bisector. So AD over DC, so these two parts that are being made by the angle bisector, is equal to AB over BC. All right, so let's look at one of these. So if KM in all of these is an angle bisector, we want to solve for X. So we're going to set this up as a ratio of the pieces created by the angle bisector. So maybe I'll go 4.8 over X. And then that's equal to the ratio of the sides that are kind of next to those pieces. So since I went 4.8 over X, I want to go 12 over 18. All right, so we cross multiply here, and that gets us 12x is equal to 86.4. And then if we divide both sides by 12, we get 7.2. So that's our answer there. I'll also want to look at one more. Let's look at number 9 here. And let's look at maybe how we can set this up. So we are not actually given this piece ML here. So we need to create that piece, or figure out the side of it anyway. And to do that, we know that the whole thing is X, and then we're taking 12 away. So we're actually going to call this X minus 12. So that piece ML is X minus 12, and now we've got something that we can make a ratio out of. So let's go ahead and set that up as, let's see, we'll go 12 over X minus 12 is equal to, and now I need to pick the side near the 12, so that's 18, and the side near the X minus 12, so that's 30. And actually, before I cross multiply, I'm going to go ahead and reduce these. So let's see, 18 over 30, we can take a 6 out of both of those, and it becomes a ratio of 3 to 5. So I'm going to go ahead and cross multiply from the far left to the far right. And that's going to get me 3x minus 36 is equal to 60. And then from here we get 3x is equal to 96. And finally that means that x is equal to 32, and that is our answer. Okay, that's all I've got for this unit. I'm going to leave the rest of the examples for you to try. If you get stuck on any of them, make sure you ask me, and I'll see you in class.